Hello guys, I'm back again. This time I will be showing you a procedure on how to assemble the structure stiffness matrix in the form of an illustrative example given here. Um, and we will try to use again the MathCAD language to just help us. Of course, the procedure will not be different if you are using a manual solution or any other program. But just to facilitate the computation in this video, so I'm using a MathCAD tool to give me automatically the values that are needed for the said assembly procedure. And this does not only show you the procedure and the assembly, but it shows you the entire uh, major step in performing a stiffness matrix solution. Of course, is this just a part of the solution to the dynamic analysis, but this is quite very important for us to know before we can proceed with the rest of the discussion. So the assembly of the structural stiffness matrix or the system stiffness matrix is simplified here in this presentation. Okay, so when I talk of structure stiffness matrix, I'm referring to the whole system, which is global in its nature. Okay, so global and structure and the system means the totality of the whole structural stiffness, which is assembled in a way for us to use it on the stiffness equation and thereby obtaining your value of displacement u. Okay, so if we know k and we know the p, okay, so we can solve for the unknown displacement u. Okay, so we're still on the step of determining the k or assembling the k value, but this is actually the hardest part into which your stiffness equation or stiffness solution uh, is used to analyze structures. So given here is a cantilever beam which is divided into three beam segments. So of course this is rather uh, arbitrary on the part of the one who is analyzing. So kung ilan yung segments na gusto niyang uh, hatiin do sa system niya, no? Okay, so the first step is to discretize the structure, and this involves the following. First, we divide, okay? We divide it into three, and then, as given in the problem, of course, and then this three subdivision is known as the subdomain. This is the total domain, global domain, and these are the local domain or the subdomains, okay? Or simply the elements or the members. After which we number the nodes. So the nodes are numbered in terms of a circular enclosure: 1, 2, 3, and 4. Okay, so this nodal numbering is just for us to be able to look into the connectivity. Okay, but it is this numbering, nodal numbering, is less important than the other numberings. What is more important here is the element numbering or the member numbering, which is enclosed by a triangle, and the nodal coordinate numbering. So there's a difference between a nodal numbering and a nodal coordinate numbering. Okay, so this is the nodal numbering, and these are the nodal coordinate numbering. So that's why I don't use the word nodal in this. I normally use the word DOF numbering. Okay, so I use a much better word, which is a DOF numbering. So from the point of view of my discussion, I will use the word DOF. Okay, so how do you number it in terms of the nodes, the elements, and the DOF? So you can number it the way you want to, but it's very critical to number the DOF. Of course, the nodes must be numbered sequentially to avoid any confusion, and so with the members. But in the nodal coordinate or the DOF numbering, the uh, the numbers which are 1, 2, okay, 3, 4, 5, 6, 7, 8 constitutes a way on making your stiffness matrix compact and unsparse. Okay, so if you have a sparse matrix wherein the elements are spread, no, it's really very confusing on your part to check it manually. Even in the program, you might be confused. Okay, so in order to avoid sparseness and make the bandwidth smaller, so you might as well group, no, your coordinate numbering, separating the constrained and the unconstrained DOFs. Okay, so what is a constrained DOF? So a constrained DOF is a degree of freedom wherein there's no movement at all. So this is a constrained DOF. Actually, class, in other references, they use the number 0 to make, okay, convert this to 0, which means this has no movement. Okay, and make your unconstrained or your free numbering, your DOF, degrees of freedom, or kinematic movement. There's kinematic movement in this nodal coordinate. You make them very near to each other. You can number them 1, 2, 3, 4, 5, 6, or 1, 2, 3, 4, 5, 6. But this is a better way to number it because they are actually sequential. No, you don't go move back and forth like that. If you do that, again, sparseness in your matrix will happen. Okay, so that's the key to the first step. And of course, you take note of their material and dimensional properties to solve for your elasticity and your uh, inertial forces, inertial properties, I, and of course your length, dimension, L. Okay, for step 2, the procedure is actually the procedure we have done a while ago, wherein we derive the local stiffness matrix for the member. Okay, so which we have done for a beam flexural element. The matrix was already ready for us to use, so we only need to prepare it. So for step 3, this is now the final step for the assembly. We use the connectivity principle to assemble it and make use of it in terms of an interactive program, or maybe a very structured programming will actually help you do it by considering the principle of connectivity in the assemblage of your structure K matrix. Okay, so take note that your capital K, when I say a big K here, I'm referring to a global or structure or the system matrix. Okay, when I have a small k like this, I'm referring to a local, a member, or an element matrix. So the above steps can actually be understood by having an example here, or solving the example, in which step 1, the numbering has already been defined. Okay, and take note that again, the DOF numbering should be done in such a manner so as to separate the constrained DOFs from the normal DOFs or the free DOFs. And the DOF size defines, or the DOF actually defines the size of your structure stiffness matrix. Okay, so how do we look into the size of the structure stiffness matrix? We just count all the nodes, the nodal coordinate or the DOF, it's 8, and subtract the constrained 8 minus 2 is 6. So your size of your structure stiffness matrix is a 6 by 6 matrix. Okay, so we expect your structure stiffness matrix to have 6 rows and 6 columns. Okay, for the given properties of your material and your element property, we have L equals 1 meter and EI is equal to 10 to the 7 Newton meter square. So they are consistent in terms of the Newton meter units. Okay, so we now prepare the local member or element stiffness matrix, small letter K. So this is K1, K2 for the member. And readily, I just plug in my formula, which I derived a while ago, and then everything will be solved or computed. So no need to worry about computing it one by one. That's how helpful MathCAD is. Okay, step 3. If you use the connectivity principle, you set the location vector for each member element. So this is very important in programming, although it's not important when you do it manually, but it helps a lot in making your solution systematic. So if you want to have a program to map, okay, you are mapping, again we are mapping your K, small k, or sorry, big K is mapped from your small case. Okay, so you have to map it, and the location vectors is a mapping matrix. Okay, it relates your case, small case, to your big case. And how do we identify what's the location vector? For element, the location vector is simply the numbering in which your local stiffness matrix is arranged. Okay, so from a local point of view, we have this numbering. Okay, so this is local. And from the global point of view, we have this numbering. Okay, example. If I have here my element 1 in the global context and the local context, how do you number them? So this is the numbering of the local is 1, 2, then 3, 4. And the numbering in the global, you look at the figure above. Okay, it's 7, 8, 1, 2. Okay, so this is 7, 8, 1, and 2. But we said that your 7 and 8 can be assumed to be 0 and 0 because they are constrained, such that your location vector now for element 1, okay, so this is element 1, is 78112, okay, which stands for 1, 2, 3, 4. It does not change. Or 0, 0, 1, 2. So is true with element 2. It's local 1, 2, 3, 4 and global 1, 2, 3, 4. And for element 3, correction, it's local 1, 2, 3, 4. Always the local is 1, 2, 3, 4. And your global is 3, 4, 5, 6. Okay, so that's the use of the location vector to come up with a very accurate and consistent connectivity procedure. So notice that for element 1, the DOF number 7, 8, which are constrained DOFs, may be numbered 0, 0 so as to indicate no movement, and all the stiffnesses values for which the row and the column numbers corresponds to the constrained DOFs are automatically discarded from the assembly process. Okay, meaning to say, if I want to assemble a 0012, I don't care about the elements of 1, 2, because 1, 2 is not a part of the DOF, which is a free DOF. It is a constrained DOF, there's no displacement, there's no rotation, so I will not consider the elements of that matrix to contribute, no, to the superposition effect of your stiffness assembly. Okay, so take note that the structure stiffness is a 6 by 6 matrix in this form, numbered in terms of row and column. And the first element of the first row, K11, read as the stiffness of DOF I equals 1 and J equals 1, receives contribution from the element 1 and 2 using connectivity rule, so that the contribution of the element 1 in K11 is K33 of element 1, and the contribution of element 2 in K11 is small k11 of element 2. So what does this mean? No? So if I will draw now if I want now to get my capital K11, which is the first, okay, the first cell on the first row of your structure stiffness matrix, I need to draw the local and the global. Okay, so what is your local K11? So if I will take a look at the global first, okay, so I divide this into 3. This is the global. Where's my capital K11? My 1 is this one. Okay, so this DOF 1 is connected to element 1 and element 2. Okay, so I'm only interested with K11. So no other DOF concerned. It's because it's K11 global. Okay, so this is your global definition. So element 3 is not connected to 1, 1, so I discard it. I have only 2 elements, and that is element 1 and element 2. Using connectivity rule, so K11 is a contribution of what? So I will now draw my local. So my local is, let's put it below. Okay, so this is 1 local, 2 local, okay, 3 local, 4 local. Okay, so for element 1, my contribution to 1, 1 is actually the 3, 3, because these are the translational, no? 1, 1 corresponds to 3, 3 of your element 1. Okay, 3, 3 of element 1. Okay, and for element 2, which is 1, 2, 3, and 4, we have okay, so this is element 2. Your connectivity okay, is actually 1, 1 of element 2. So 1, 1 of element 2, such that if we add the 2, we add the KT3 of element 1 and K11 of element 2, this will constitute now your K, capital K 1, 1 of your structure stiffness matrix, which is simply this one. K33 of element 1 and K11 of element 2, which is what? A 12 EI, if you will look here. Okay, 3, 1, 1. So this is the one. K33 of element 1. Okay, and a K11 of element 2. You add 12 plus 12, so you get 24 EI over LQ. Okay, so that's the just the first. So the second element of the first row K12, this one, where the stiffness of DOF I equals 1 and J equals 2, receives contribution from the element 1 and 2 using connectivity rule again. And the contribution of element 1 in K12 is small k34 of element 1, and the contribution of the element 2 in K12 is small k12 of element 2. So this is still the same global and local connections. Okay, so these are the local connections. But now we are not referring to a 1, 1, but rather a 1, 2. So we draw the 2. So that's your 2. Okay, look, 1 and 2 is still connected to node 2 such that the only contribution it can get is from 1 and 2 members. Okay, so what is now your connectivity of 1, 2? So you are now considering a connectivity of 3, 4 of element 1 and a connectivity of 1, 2 of element 2. So that's why you get again the connectivity of 1 of 3, 4, which is negative 6 of element 1, and a connectivity of 1, 2, which is positive 6 of element 2. If you add the two, negative and positive, the amount will be 0. Okay, so that's how to deal with K12 and so on and so forth. So you just do the same. So there are several more illustrative examples here on how to get the third element of the first row K13 read as a stiffness of DOF I equals 1 and J equals 3. So it's receiving again the contribution from element 2 only. Okay, why? Because if you look at this, let's not draw it. You just look directly on the figure here. Okay, because the connectivity principle is simplified by simply looking at your figure. So we are now on 1 and 3. So the connectivity of 1 and 3 is only contributed by one member, which is member number 2. Okay? And that member number 2 has a local coordinate of 1 and 3 also. It so happened that they are the same. So capital K13 is now equivalent to the contribution of small k13 of element 2, which is simply 1, 3, which is simply 12 EI over L cubed, such that if I plug it here, I get 12 EI over L cubed. Okay, that's a negative sign, class. If you look here, You might be confused, so that's a negative sign there. Okay, so negative 12 EI over L cubed. This is automatically drawn, no? Hindi siya manual, kaya I'm confident that hindi ako masyadong magkakamali, no? Although may mga typo errors, pag nag-typo error ka, mamamali siya. Pero automatically, if you're typing accurately, the answers will be accurate. And the procedure is repeated time and again, ulit-ulit, again, using similar procedure, we can now get the assembled structure global stiffness matrix K in this form. Okay, so take note that I only get the upper triangular matrix because this is symmetrical, and then the lower off diagonal matrix will be simply the same as that of the upper off diagonal elements because of symmetry, and the values are readily solved by simply plugging in the formula, and then you get K equivalent to this one here. Okay, of course, what I did is I summarized K1, K2, and K3, and then just look at the connectivity here without regard for my a figure. So I just have my location vector. LV here is a location vector 0, 0, 1, 2, which simply defines where is your constrained DOF and unconstrained DOFs. Okay, and this also defines you the exact location of the cell to which your contribution will be obtained, will be uh, added to, no, to the structure stiffness matrix. Okay, you can also think of assembling it this way, no? If you have used the elements, you can simply look into the unconstrained DOFs and look at this. 1, 1 here simply means that 12 EI over L cubed contributes to K11 of your global stiffness matrix as far as K1 is concerned. Okay, so if I will count, how many elements contributes to K11? So I can now check it. 1, 2, and wala na dito. Wala nang 1, 1 dito. Kaya 1 and 2 elements only contributes to the K11. Another way of thinking of it is what is K12, capital K12, what elements contribute to capital K12? So if I read this 1 and 2, so this negative 6i over L contributes. I have also 1 and 2, this positive 6ei also contributes, but here there's no 1, 2. Okay, and so on and so forth. How about capital K25? Okay, so I just look. 2, there's no 5 here, so this does not contribute. 2, there's no 5 here, this does not contribute. Okay, so 2, there's no 2 here, this does not contribute. So K25 is automatically 0. That's why you will see here 0 values. K25 is 0. Okay, so this connectivity procedure is actually a very easy guide to programming class. If you know how to program it, you can deal with this in any type of member, flexural, axial, torsional combinations. You can use it in plate elements, you can use it in solid elements, and you can just do it in MathCAD. Of course, if you know high-level language programming better, but MathCAD can do it. Okay, so if you have a particular solution, a particular material for research involving this, you can actually modify some elemental consideration by adding a spring here, adding a partial fixity here, adding so there are a lot of things to research about structural engineering. The only problem it's really very difficult, time consuming, and sometimes expensive to do it. That's why we all need to sacrifice a lot in terms of time, effort, and money for us to be able to contribute to the progress of the structural engineering profession. Okay, so I hope that you have been enlightened with the very simple procedure. I'm doing this because I don't want you to be reading a lot of very complicated explanation in the book on how to deal with it. This is the simplest way I can deliver how stiffness matrix assembly can be done um, uh, using this very simple example, of course, but it can be used very effectively on complicated systems, especially in dynamic analysis. Thank you, and I'll entertain questions maybe after this video.